Buon pomeriggio, io sono Tommaso e faccio parte di WeScience, il gruppo giovani di Bergamo Scienza. Le conferenze della 23esima edizione di Bergamo Scienza sono rese accessibili a persone con disabilità motorie e sensoriali, garantendo luoghi privi di barriere architettoniche e servizi di traduzione LIS. Tutte le conferenze sono videoregistrate, alcune delle quali trasmesse anche in diretta streaming. Le conferenze con ospiti stranieri prevedono la traduzione simultanea. Le registrazioni verranno pubblicate sui nostri canali ufficiali al termine del festival. Questi servizi sono resi possibili grazie a Fondazione della Comunità Bergamasca e Fondazione Banca Popolare di Bergamo, che, insieme a Bergamo Scienza, sono impegnate a promuovere inclusione e accessibilità. Per la traduzione simultanea è sufficiente scannerizzare il QR code che vi possono fornire i volontari in sala o che trovate proiettato alle mie spalle. Il QR code vi indirizzerà direttamente a Converso Web App, dove potrete selezionare la lingua di interpretariato dal menu a tendina. Per l'ascolto della traduzione è necessaria una coppia di auricolari. Vi chiediamo la cortesia di utilizzare le vostre. Chi ne fosse momentaneamente sprovvisto può chiedere ai volontari in sala. Vi ricordiamo che alle ore 17 ci sarà l'incontro moderato da Elisa Riceputi, dell'Università degli Studi di Bergamo, con l'intervento di Chiara Montanari, Life Explorer, che condividerà la sua esperienza in Antartide per riflettere su come prosperare in condizioni estreme, imparando a gestire l'incertezza e a prendere decisioni lucide e coraggiose anche nei contesti più imprevedibili. Vi do il benvenuto all'evento di questo pomeriggio, intitolato Umani che mangiano batteri che mangiano CO₂. Avremo il piacere di ospitare come relatore Ron Milot, Weizmann Institute of Science. La conferenza sarà moderata da Telmo Pievani di Fondazione Bergamo Scienza. Vi preghiamo di silenziare i vostri apparecchi elettronici e di partecipare numerosi alle iniziative di Bergamo Scienza. Grazie per l'attenzione e buon ascolto.
Grazie, benvenuti anche da parte mia, grazie di essere qua. Allora, l'incontro di oggi nasce in un momento abbastanza preciso. Nel 2020 era l'anno pandemico, noi a Bergamo l'abbiamo vissuto come ricordiamo tutti, ahimè, ma uscì in quei mesi anche un articolo scientifico che fece grande scalpore, uno degli articoli più citati poi negli ultimi 5 anni, il cui ultimo autore era proprio il nostro ospite di oggi, Ron Milot, che ringrazio tantissimo di essere qua. Lo abbiamo chiamato, atteso e l'abbiamo cercato in tanti anni da allora, è finalmente nostro ospite e siamo onoratissimi di averlo qua. Perché è così importante questo articolo? Già dal titolo era molto semplice. La massa di tutto ciò che è stato prodotto dall'umanità, degli oggetti umani, degli artefatti umani, nell'anno 2020 ha superato la biomassa. Detto altrimenti, nell'anno 2020 il peso di tutte le cose umane, di ciò che noi produciamo, i manufatti umani, gli edifici, le suppelletti, le strade, i mezzi di trasporto, la nostra civiltà, come peso ha superato quello di tutte le piante, gli animali, i microrganismi messi assieme. È uno dei tanti esempi di lavori di Ron Milot, quantitativi, basati sui numeri. Lui è un grande esperto di biologia e di ecologia e di biologia dei sistemi basata sui numeri, calcola le cose, pesa tutto quanto, e quell'articolo è importantissimo, potete anche leggerlo perché non è di difficile lettura, spiega che cosa è successo, come siamo arrivati a questo risultato. Tra l'altro 2 cose soltanto, ma poi ne parlerà lui tra poco. Nel 1900, 125 anni fa, la massa antropogenica, cioè di tutti gli oggetti umani, era il 3% della biomassa, il 3%. In 120 anni è diventata la raggiunta, è diventata il 100%. Quindi vi rendete chiaramente conto della grande accelerazione della civiltà umana, dell'impatto sull'ambiente, delle cose umane negli ultimi 120 anni. E poi hanno calcolato la composizione di questa massa antropogenica, principalmente cementi, mattoni, sabbie, asfalti. Noi siamo la civiltà dell'asfalto e del cemento. Ma Ron Milot negli anni seguenti ha pubblicato anche, ve ne cito soltanto alcuni, un articolo complicatissimo dove hanno calcolato il peso di tutti gli artropodi, per esempio, cioè di tutti gli insetti, crostacei e tutti i gruppi che fanno parte di questa grande famiglia degli artropodi, difficilissimo conteggio perché è una biodiversità estremamente diversificata. Hanno calcolato quanto pesano tutti i mammiferi selvatici. Qua ce lo ridirà lui, ma è una cosa molto triste perché tutti i mammiferi selvatici sono ormai un'esigua minoranza rispetto a tutti i mammiferi. E gli altri mammiferi chi sono? Siamo noi, esseri umani, e soprattutto gli animali che rinchiudiamo negli allevamenti intensivi. E poi, meraviglioso, nel 2023 hanno calcolato con il suo gruppo la massa totale, il numero e la distribuzione delle cellule del sistema immunitario. Visto che non ne parlerà, credo tra poco, se vi interessa, sono 1800 miliardi di cellule, quelle del sistema immunitario, e in totale pesano 1,2 kg. Okay? Questo è quello che pesa il vostro sistema immunitario. A questo punto vi chiederete, ma perché fare tutti questi conti? Dove vogliamo arrivare? Beh, perché lo vedremo tra poco, fare questi conti serve per capire le soluzioni a quello che è evidentemente un problema, soprattutto rispetto al primo articolo che citavo, no? Non era mai successo nella storia umana che una specie producesse degli artefatti che vanno a riempire tutti gli ecosistemi e a pesare tanto quanto tutta la vita sulla Terra. Visto che siamo a Bergamo, lo ricordo anche a Romilo, qui ha vissuto gli ultimi anni della sua vita Giulio Natta, premio Nobel per la chimica nel 1963, insieme a Carl Ziegler, il quale, quando inventò i suoi meravigliosi polimeri da cui è derivata la plastica che conosciamo noi oggi, innescò un dibattito che si intitolava "Hanno scoperto il materiale che Dio si era dimenticato di inventare". Frase molto ad effetto, che da un lato voleva dire che avevamo trovato un materiale molto democratico, che costava poco, flessibile, duttile, che aveva ridotto tantissimo i costi industriali nel produrre gli oggetti, ma dietro c'era un lato oscuro, che a quel tempo non si poteva ovviamente calcolare, e cioè che quel materiale viene poi usato, gettato nell'ambiente e non ci sono batteri che si sono evoluti per ora per mangiarlo, per digerirlo. Quindi immaginatevi cosa potrebbe voler dire se scoprissimo il modo per fare evolvere dei batteri in grado di digerire la plastica, oltre che produrre bioplastiche che poi si degenerano da sole e si sciolgono nell'ambiente. Leggevo qualche giorno fa un paper che probabilmente Ron ha letto, è uscito su Nature Medicine, impressionante, dove è stato calcolato il bioaccumulo di microplastiche nel cervello umano, i cervelli defunti naturalmente, e se vi interessa la quantità di polietilene che è contenuto nel nostro cervello assomma all'equivalente di 7 grammi, che sono circa 2 tappini di plastica delle bottiglie, in ognuno dei nostri cervelli, microplastiche. Quindi quello di cui si occupa Ron è un tema enorme, gigantesco, importantissimo per la salute umana e per la salute dell'ambiente. Ecco perché parliamo di batteri che noi possiamo mangiare e che a loro volta possono mangiare altre cose, per esempio plastiche o CO₂. Ron, è già stato detto prima, lavora al Weizmann Institute, è un grande esperto di Systems Biology, che è un grande filone di ricerca oggi, è la biologia che si occupa dei sistemi, appunto, e oggi parliamo veramente di sostenibilità, ma lo facciamo in modo molto concreto, quantitativo e affascinante, usando il linguaggio di Ron, che non deve spaventare, è il linguaggio dei numeri, delle quantità, ma vedrete che come lo fa lui è un modo potente anche da un punto di vista narrativo. Tra l'altro, una curiosità, Ron col suo gruppo ha creato lo dico anche agli insegnanti presenti e ai ragazzi, un sito divulgativo molto bello, che si chiama anthropomass.org, con il TH, massantropica.org, dove trovate un sacco di informazioni con delle visualizzazioni grafiche molto efficaci e con tutte queste comparazioni, quanta plastica c'è rispetto agli animali, quanto pesano gli edifici rispetto alle piante. Scoprite che tutti i pesci che ci sono nel mare pesano come la singola città di New York e cose di questo tipo. Una che mi ha fatto tanta tristezza, il peso di tutti i rinoceronti bianchi rimasti sulla Terra, tutti insieme, se li mettete su una bilancia, pesano come la singola Tour Eiffel ormai, quindi sono veramente pochissimi. Ecco, questo è il mestiere affascinante che fa Romilo, a me piace tantissimo, l'ho sfruttato tantissimo nei progetti di divulgazione e mi piace molto che stavolta invece parla lui direttamente e lo ringrazio tantissimo. Grazie a te.
Thank you very much. Okay, hello everyone. Should I start? So I hope the expectations are not too high after this very kind introduction. I'm delighted to be here in your beautiful city and the beautiful festival that you have here. And back home, whenever I want to enjoy beauty, I usually go out to nature. This is how things would look in the spring back home, and probably also here when you go out into the hills. And this is also the place where I also go when I want to be inspired or when I want to make new friendships. So nature gives us so much in all of those respects. At the same time, as was mentioned here and as we know from different directions, the ability to enjoy that also for my daughters and even myself, let's say in 10 or 20 years' time, is under danger. And this challenge is something that I want to spend my time trying to think how to balance properly. And this would be part of what we'll be talking about today. And when we're talking about the many capabilities that we have as humanity, we really need to go into the basic source, into what drives all of these fantastic capabilities that we have. And when you go to the, as scientists, we want to understand really the essence of where things are coming from. When you want to start from the beginning, you have to look beyond this and really look up. Because really, much of what enables us to drive our society is based on the energy of the sun. And we have a wonderful place in the universe, which shows a great real estate, if you like. We are in a place in the solar system, such that in every hour, the energy coming from the sun is what humanity uses in a whole year. Okay, so every hour we get from the sun the energy that could drive us for a whole year. It's always interesting for me to think about that. And now the question is whether we're able to use it efficiently. And this is a big challenge for nature and for us, humanity. And when you're thinking about energy, we're also at a very interesting time in the history of humanity. Because it's usually, if you want to give a talk, it's not good always to just talk. You also want to engage. So let me ask you a question. The best way to get energy these days is through electricity, right? So if I asked you, what fraction of humanity now has this wonderful thing that they could connect and get electricity? So in order to make that concrete, let's ask that question in a very clear way. Would you say we are now at about 30% of humanity that has electricity available to them, 60% or 90%? Question is clear? Let's do a quick raise of hands. Who's voting for 30%? I would say about a third. Who's voting for 60%? About a half. Who's voting for 90%? Myself and a few people. Okay, first of all, we see it's a very liberal crowd. We have all the answers. You're all over the place. Most of you are wrong, which for scientists, this is a very good thing. I see people smiling. I see there's very intelligent people. When you're wrong, you're learning something new. So that's excellent. And the answer today, I would say very happily, is that we have the fantastic thing that came through science and through technology that now 90% of humanity has electricity available to them. Maybe not as easily as the people of Bergamo, but still this wonderful achievement of humanity. And for that, I think we should always be thankful. And in general, I would say, in all the challenges that are in front of us, we should always look at those two different things. In a way where in the best of times, like if you had to be born, to choose a time to be born, and you wouldn't know whether you'll be born to a noble person, somebody in Bergamo, somewhere else, or just, some farmer somewhere in the world, the best time to be born, I would say, would be now. You wouldn't want to be born 100 years ago or 1,000 years ago. So we are in the best of times in many ways. And as I will also show, in many ways, we're also in the very most challenging time to be born in, because there's many, many challenges. So with that power, there's also lots of challenges, I would say lots of responsibility. And in that spirit, I would say that the energy that we're currently, in order to make the electricity, it doesn't come from the sun. The majority is still coming from fossil fuels. So if you go back to the sun, it's really energy that's coming from the sun, but that came millions of years ago and was stored in plants and other organisms, and we could now take it out of the earth. And we're doing it at a fantastic rate. Every year, we are burning what accumulated over 1 million years. So this also shows how, in principle, we could use the energy from the sun, and it supplies so much, but we are using something from millions of years ago, which is available to us, and we're burning it very quickly. So there's a challenge here. And this is also what's giving us an ability, the fact that I could come and visit you, transportation, is really currently still based mostly on that, although we have more and more electric cars and other modes coming up, but still, this is driven by fossil fuels. And also, the ability to enjoy, Bergamo and the festival not only during the day, but also during the night, is based on the fact that we could light our cities, and it was beautiful to be yesterday at your old city and to enjoy all that. So really, this ability to work at day, at night, it's all based on those fossil fuels and more on renewable energies. And really, this is the challenge, because what we're currently seeing is that the result of using those fossil fuels, what you see here is a depiction made by NASA of looking at the temperature of the Earth every month of the year in the past over 100 years. And you can see we are in this small range, but now in recent years, we see very clearly, empirically, that we reached a point where the temperatures are much higher than they used to be. You see we're going out, and those temperatures are now, the rate of change is the fastest for the past 66, like in terms of rate of change, in the past 66 million years ago. Anybody knows why 66 million years ago? What happened then? So, at that time, the things that ruled the Earth, kind of like what we're doing now, were the dinosaurs for hundreds of millions of years. And they thought everything's great and they could stay the dominant species around. But then a meteor came, and the change of temperature that it led to was the last time that was fastest than what we're doing currently. And it didn't end well for the dinosaurs, and now it's on us to think how to handle this so that we'll do better than them. So this, I would say, is the grand challenge of our decade and our generation. But I would say at the same time that it's a big challenge for keeping nature intact, it's also a huge business opportunity. Why is that? Because people were analyzing for what we need in order to deal with that. We need a new economy based on what's known as net zero, meaning we'll reach a situation where we have new capabilities to do things. And the amount of money that's associated with that new business and industry was estimated to be this number. And I really like numbers, so I'm usually enjoying looking at numbers. And this number, I think, actually even surprised me, because anybody knows how much this is? It's so much that I see people counting the zeros. Maybe I could help you with that. So maybe this could help a bit. So it's really such a huge sum. This is $300 trillion between now and 2050, the time that we're aiming for to reach net zero, which means that every year there's a business opportunity of about $10 trillion. That's a huge opportunity and shows us that we also have a lot to gain if we understand how to move forward from here. And the way we're approaching this is, in many different ways. Back home, we've been working a lot about solar energy in different novel ways. And there's really cool ways to do it. This is one of them. Another relates to another very cool method, which is how to gain energy directly from solar panels. I think this is actually not far from here in Lausanne. But I think the most inspiring way that I saw about how to take solar energy and to use it efficiently, I actually enjoyed seeing it even just outside of this lecture hall not long ago, when I saw your beautiful flower and plant market that you have every Saturday. And so this technology was invented by nature, and this is plants. Plants have the capability to basically grow based on solar energy, and I always enjoy seeing them develop. And I think we could take inspiration by trying to be as efficient in trying to achieve the things that we need to thrive, similar to how plants do it. And humanity has already been very smart at learning things from plants. Learning, for example, how to use them for food. And what you see here is a depiction of the number of people around the earth that were under extreme hunger, and how this number has been decreasing very clearly for the past several decades. If you take the numbers here, you would find that every day for the past 30 years, about 200,000 people on average a day came out of extreme hunger. If you want, I don't know what's the newspaper that you tend to read, but this could have been the headline every day in the newspaper of 200,000 people, coming out of extreme hunger. Every day, this is the news. And I would say this is the big news of the last 30 years. I don't know how the newspapers in Italy go. Back home, the titles tell different stories. But I think this is really something that we should remember, how lucky we are, and many people around the globe, about the fact that this is what technology brought us. But this challenge, how did it come about? It came through the ability that came through science to increase the yields of how we use plants. So there's this thing called the Green Revolution that tripled the yields that we're getting from our fields. And with that, we could make sure that we don't have extreme hunger because we have this abundance. But the fact that we were able to achieve this does not tell us exactly how do we deal further on, because now we have more people, we have better standard of living, and we have things that our nature is adapting to this in a way that now there's new challenges. For example, you have many places around the world where how we're doing that higher yields leads to desertification or to soil erosion. So there's many different challenges, some of them coming also from the changing climate, and we need to find new ways on how to still give us the ability to get food and other things. And in that respect, we have to think about the next green revolution. And we don't know, because here it seems like in this direction we did as much as we could. So we have to think about novel ways that science and technology could take us from here. One of the research directions that we're exploring is to try and do that with something that facilitates new ways of growing food. And I'll be touching on that in the second part of my talk. But for now, I would say that many of those challenges requires the kind of approach that we have in the Institute of Environmental Sustainability, something that I'm heading, which looks at all the different challenges and trying to put scientists to give them the capability to work on things related to renewable energy, to food security and nutrition, sustainable materials, climate research, environment and health, marine research, and biodiversity and ecosystems. And let me touch now on a specific research that was mentioned before that deals with this issue of biodiversity and ecosystems before we go back to our food. So far, so good. If anybody wants to know, I know it's after lunch, so we could take a stretch. Maybe that's a good point just in the talk, so, or breathe. It gives you, it's part of the, body, mind, so that you can learn more from what we're talking about. Good. So let's talk about that. And I like to take a concrete angle into thinking about those things. Let's ask a question. Which group of living things dominates global biomass? When I mean global biomass, I'm saying if you put all the organisms on some weight, would it be, and you already understand, I like asking you questions, so let me ask the following question. Would it be A, that would be bacteria, B, it would be fungi, C would be plants, and D would be animals? The question is clear. We talk about what weighs the most on Earth. And we want to keep the ability of, democracy, so let's vote once again. Who's voting for A, for the bacteria? Almost everybody. Who's voting for fungi? Okay, there's some people in the back that really like fungi. Who's voting for plants? I see a few for the plants. And who's voting for the animals? A few. Great. So First of all, I would say I noticed some interesting, maybe it's for social scientists, I think some scientific phenomena. When I asked the question before, people raised their hand like this, and now they raise their hand like this. I don't know what's happening. It seems like people, are losing their confidence. That's fine, and I would also say that makes sense because, again, most of you are wrong. But I see, again, people are smiling, so you're going to learn something new. So, okay, you came for the right thing. This is what they promised you anyway. You ready for the answer? Okay, so let's reveal the answer. So what you see here is really the depiction. If you took all of the living things on Earth and you put them on a weight, what would be the composition between the different groups? And you can see one big sector. The sector is proportional to how much mass it has. And that sector in green, oops, sorry for a second. Aha. Okay, some of you might have noticed already. The sector that you'll see here in green, anybody wants to guess? Anybody knows now? So the fact that it's green is not completely a coincidence, because we like using colors in a way that would be intuitive for communication, and that would be plants. So all those who voted for bacteria, don't worry, you're in second place. Quite far behind, but still in second place, that's, I think, fine. And fungi are in third place. So the story of really, the biosphere, the things around us in terms of what is in there, it's really the vast majority is really plants, 90%. Second place is bacteria, and then everything else. And then you might ask yourself, what about us? What about humanity? So humanity, you can see them here. It's this 0.01% of biomass on Earth, this dot that you have there, which I would say begs the question, how much effect does this 0.01% has on the rest of the things, right? So this is really what drove us forward in the research. So the guy that was able to do that is this guy, Yinon Baron. He was able to do this quantification of all the biomass on Earth. And he could, and in the effort, we could look at the effect of humanity, this 0.01%, on all the living things. Let's say, for example, let's take mammals. Mammals are very close to our heart. We usually know them very well. The bedtime story that we read to kids are usually about all sorts of mammals making friends. So how much, if we looked at, would be the mass of domesticated mammals versus wild mammals, all those mammals we see in, BBC documentaries or nature movies? So the answer is this. This would be us, this would be the livestock and us in terms of biomass, and all the wild mammals combined, not only the special goats that you see here, but also the wild elephants and the whales and the antelopes, all of them together would be just 5%, which I think shows us the perspective, and the ability to do this is based on the work of Lior, a PhD student in the lab that was able to do this census of life. Which leads us to something that was the follow-up. After we did this census of life on Earth, we said, hey, we know now the mass of all the things that are living on our planet. What about the things that we are making? Also known as anthropomass or anthropogenic mass. This is everything from cell phones to cars to buildings or roads that we make out of, either concrete or something else. This is rapidly rising, whereas the mass of things that are alive, this is kind of constant, maybe going down. And then somebody, if you know that, if there's a function that's going down or stable and a function that's going up, at some point they're supposed to meet each other. And we ask ourselves the question, when would they meet if you have these two things? And the answer that we found is what you see here, is that indeed one was rapidly rising and one is relatively constant. And the year 2020, just a few years ago, is when those two functions met, which, as was mentioned before, is really the time at which if you had an alien coming to planet Earth and was just solving it from a distance, they could find there's more of human-made stuff than all the living things combined. If you want to take more concrete examples, you could look, for example, at the weight of all the plastics, which I've now learned, much of it thanks to inventions made here, has now superseded the mass of all living animals on Earth. And similarly, you could look at other things like the weight of buildings of concrete, now more than the weight of all the trees and shrubs that, as we said, is like 90% of all living things on Earth. And the question of how to deal with this challenge, how to find the right balance between those things is really what occupies me and many, many scientists from around the globe. These are the sort of efforts that I was mentioning here of trying to look at those things from all of the different angles in environmental sustainability. And within that, I'd like to share with you one specific research direction that I think would be of relevance and interest. So I'll move to that. And this is in the spirit of opening our minds to new directions. I want to talk with you about this question of how to transform our diets to be more sustainable. And again, here you would like also to start at the beginning, to think, okay, where does our food come from? How does that all work on a global level? And there, it's good to remember that the world is really broken down. If there's a way to solve this, maybe I'm doing something wrong. Okay, that feels a bit odd. Is it better this way, or I can continue this way? Okay. So the world can be broken down into things which are producers. What you see here, where it takes energy from the sun and gives you biomass. And the second part would be consumers, those that take the biomass, sort of like us, but also giraffes, that take that stored compounds and are the consumers of that. And what we asked ourselves is whether we have the ability to turn these into those. What do I mean? The way this works, and this is really at the basis of our civilization, is that we have energy. We have energy coming from the sun, and nature found a way in order to take that energy. You remember we talked about the lots of energy coming, and the elegant way that plants do it is that they use that energy and they store it in the form of sugars by using the sort of things that you see depicted here. And that leads to growth. And we wanted to see whether we could also harness that directly. And the way we're trying to do that is to try and think if we could change the diet of this guy, E. coli. It's an organism, the one that we know, it's a small bacteria, usually lives in our guts, and it's the one that we study the most in labs around the world. If you like, that's the living things that we understand the most, better than anything else on Earth. The thing is, the diet of this organism is based on us, putting all sorts of sugar, just like the thing you might have added to your coffee over lunch. And we want to see if we could change its diet from eating sugar and releasing carbon dioxide into a diet that would take carbon dioxide and would create sugar, but not only sugar. From that you can then, in biology, you can transform it into all sorts of other things like protein, etc. So this is the challenge that we put forth. And the way to approach it is to look at really how biochemistry, which is really the alchemy of the living world, which knows how to transform materials from one kind to another, to see if we could teach E. coli to do the same type of reactions for which the Nobel Prize was given to Kelvin and Benson over how to do this thing of taking carbon dioxide and produce all those things. And we tried to see if we could teach the bacteria to do that, and for that it turns out you could put a few genes and it would have all the capability in principle in order to do this fantastic achievement. We tried to do that. We got a lot of funding from the European Council in order to do that, and we failed. We tried to do it in rational design of putting the different components, and it didn't work. But this was too late because the students were already working really hard. They have to get their PhDs. The ERC gave us the funding. We said, we can't fail now. We have to find a way in order to still solve the problem. So we had to go to the most powerful tool that scientists in the life sciences have available to them. A tool like no other in terms of problem solving, such it could already also solve the problems that we, after decades of experts studying around the world, could not understand and solve. Anybody has a guess what this tool would be? The most powerful one? So that tool is evolution, or in this case, lab evolution. So what we decided to do is to take the bacteria like this, and in order to change their diet, we did all sorts of engineering. That wasn't enough, although that was essential. And then we threw them into a machine called a chemostat that over several months does lab evolution, meaning they can accumulate new ways under a selection pressure that their diet, they only get very, very little food, not like they're feeding me here since I came, really little food. And at the same time, we're giving them lots of carbon dioxide and energy available to them. So they're really under strong selective pressure to try and learn how to make the experiment succeed, that they could change their diet. And then the hope is that one day it would lead to cells that are able to do that dietary shift. So we did that, and you wait a week, it doesn't work. You wait a month, it doesn't work. After somewhere between half a year to a year, you have to have students that are really bold and willing to wait, you start to see something. That's assuming it didn't get contaminated, which what happened during the first and second years. But if you waited long enough, you start to see bacteria that are now able to grow directly from the air, just like those things that we were looking for. And this made some people very happy, because you can see here the different students that were working on it over the years. And they could show that now you can make such bacteria that build all of their biomass directly from carbon dioxide, directly from the air. And we could even understand the basis of how this was achieved. Anybody who wants to know more deeply about it, either you can see the studies here or you can catch me after the talk. But I'm trying to give just a general overview. This is the way to achieve such a thing. From here onward, this opens the way for a future that is based on microbial production, meaning you could have bacteria that are very efficient in many different ways, and you can feed them for the diet with energy that is coming from renewable sources, such as photovoltaics or wind energy, and you can give them all of their food is coming from carbon dioxide that we want to capture anyway, either directly from the air or from our industry, and mix those two things together and have those bacteria do microbial production of what? So we want them to do high-cost foods and chemicals. Then we want to move into staple foods and feed, and maybe one day to bulk fuels. So this is the vision that we're moving towards. We have a lot of work, but I think as a community around the world, many researchers, when we started working on this, it was kind of seemed like science fiction. But now I just came from 2 conferences, one in the US and one here in Europe, that are actually actively, it became like a big field of research. Many, many different scientists are now making progress on this. We're also, I won't get into all the details, but we're looking at the environmental impacts. If we made our food in such a way, if you look at what would be the result in terms of greenhouse gas emissions, the things that are changing our climate, the land resources, how we're using all of our land, and if we want to enable to keep nature reserves, or how we're affecting water, and many locations around the world have more and more water scarcity, we could find all this in green means that it's about over 10-fold more efficient. So you can save a lot of resources in producing our food in this way. So even if you enjoy the food that you're enjoying now, I'm happy for that. We should remember that as scientists, we have, I think, the obligation to think forward and to understand that there's going to be huge challenges in the coming years and decades, and we have to build the tools and the capabilities to find a way to get a better balance between us and the living world. So this is what I wanted to share with you. I would say that in general, we live in a time of really unprecedented achievements, but also unprecedented challenges. So we should be, I think, thankful and I feel blessed that I could, travel the world, come and meet you, enjoy all the things that we're enjoying, and at the same time we have the responsibility to think how to move forward from here. A huge challenge, and I think at the essence of how we're using many of our natural resources, relates to our diet, and therefore it's very important. And we're trying as scientists to build both the capabilities, understanding of how to produce that more efficiently, and microbes could be part of the solution. In ending, I would just say this is all a big effort done for many years. So you can see here some of the people that really started this. So this is now about 17 years ago that we started this project. So this is the team that worked on it from the beginning. And being a scientist, it's wonderful because all the time you're working with young, bright people that come motivated to work on the problem. So this is the group that started it. It moved into this group. This is the wedding of one of the students that was really doing this thing that I told you in this machine, chemostat. So before it was automatic. This lady, Shira, when she wasn't in her wedding day, she really worked on doing it manually, day by day, moving the bacteria in order to change their diet. From there onward, we have another generation and another generation working on this problem. And finally, this is the last hike that we took as a group with the people working on that effort nowadays. All with the support of both the ERC, the European Union, together with our own national funding agencies. And in the end, all of this is really based on taxpayers' money that are willing to invest in science in order to give us solutions for the future challenges. So I think it really belongs to all of us. Thank you very much.
Grazie Ron. Abbiamo anche tempo adesso per una lunga chiacchiera insieme. Io ti chiedo però una prima cosa, prima di lasciare spazio a voi. If you explain us the methodology through which is possible, se ci puoi spiegare, perché è una cosa che capita spesso, la chiedono anche a me, come si fanno a calcolare delle masse così enormi e anche così eterogenee? Tutta la massa di tutti gli oggetti umani sono dal mio computer alla penna, alle suppellettili, ai satelliti, alle macchine, a quelli che passano fuori adesso e fanno casino e ci danno fastidio per strada. C'è tutta la massa antropogenica. Come fate? Qual è la metodologia per calcolare masse così vaste ed eterogenee?
Of course. So I'll be happy to explain that.
You have to use the and microphone.
So I'll be happy to do that. I would start first by saying thank you to the translators because my Italian is not very good. Even though my mother, which is with us in the audience, she knows Italian much better because she loves Italy and Italian, so she's been studying it year and year. And for her, coming here to be with you is really a dream come true of using her Italian. So I'm really happy that we also have the translation, and thanks to my parents and my mother that came to listen. And when thinking about how to do such things, it's always, I could give a general explanation, but it's really good to give a concrete example, otherwise we're getting lost. So let's say I want to know the weight of all the fish in the ocean. Okay, we actually calculated that. So, nobody would give us the permission to fish all the fish in the ocean. It's not moral, and we also don't have the funding to do that. So we need to find an alternative way, and the way to do that is really to fish the literature. Okay? So what you're doing is you're collecting data from the vast literature of all sorts of people that went into all sorts of different locations around the ocean and found what's at that specific location, what's the weight of fish at that depth and that day of the year, etc. And there's a lot of that information because scientists, they like going on cruises and collecting information, so we have a lot of such data. But of course, we didn't go all the places and in all the time. So you need to find a way to what's known as extrapolate, to be able to tell about other locations. So for that, what we're doing is we're trying to find correlations, connections, which are mathematical, between the weight of the fish, which is what you want to know, and all sorts of properties of the environment. So what kind of properties would that be? It could be, for example, the temperature. It could be the depth of the ocean. It could be the nutrients. It could be how much sunlight. It could be how far it is from land. All sorts of different things. And we're building mathematical models that connect between all the data that we're able to fish and the weight of the fish. It could be very complicated. It could be not just simple regressions, but all sorts of, black magic from the books of statistics, and most recently all sorts of machine learning and AI. But you find tools to do that. And then with all the environmental data, because the temperature at every point on Earth in the ocean, that's something you could tell from satellites. And the depth of the ocean, we also know that. So all of those environmental parameters we know very well. So with those mathematical models, we could extrapolate and then integrate, and we have a value. And then we're repeating this process again and again, not only in order to get a number, but in science, the important thing is not just to say something, but to see how sure you are that it's correct. So repeating it in different methodologies, and then get an uncertainty, and then we could tell them, there's this amount of fish, plus, minus, or how much is our uncertainty, and then it really becomes science. So this is the approach, and this is how we do it for fish, but now we could also do it for insects, and we could do it for fungi. Every time it requires some creativity of how to approach this, but this is what we enjoy spending our time doing.
Bene, ci sono domande, se no io ne ho tantissime altre. Intanto che le preparate, c'era un'altra, Ron, che mi ha colpito molto, l'ultima parte della conferenza. L'anno scorso abbiamo avuto ospite qui Francis Arnold, premio Nobel per la chimica, per la sua scoperta dell'evoluzione direzionata degli enzimi, cioè ripetere in laboratorio un processo evolutivo, inducendo mutazioni sugli enzimi e generando enzimi possibili, ma che la natura non aveva ancora evoluto. Tu ci hai parlato invece di Adaptive Lab Evolution, cioè ancora una volta un'evoluzione adattativa fatta in laboratorio. Mi ha colpito questa connessione, cioè è come se in diversi ambiti della scienza, lo dico pro domo mea ovviamente, avessimo capito che copiare l'evoluzione può essere una soluzione per le nuove tecnologie del futuro. Ha senso?
It takes a bit longer to get all the translation, and then I have to think for a minute. So the work that you were mentioning from Francis Arnold, the Nobel Prize winner, is actually indeed very much related in spirit and content. I was actually having lunch with her in California, I think, last year? And it was actually very moving for me because it was also with my daughter that came to do an internship at the same institute at Caltech, where Francis Arnold is a professor. And she came just after finishing high school, and she came for a few months to play with science and biology, which, as you can imagine, for a father, it's very rewarding to know that, his daughter is sitting with this Nobel Prize laureate and is talking with her, and maybe it gives her some role model also for the future. Sure. So indeed, what they're doing is very similar to what we were just discussing at the level of cells. They're usually doing it at the level of those machines, enzymes, or proteins that are able to do those different changes that we were talking about, that biochemistry, or if you want, alchemy that is science-based. And what we're talking about is kind of a level above it of like trying to combine these machines together into pathways that work together in a concerted manner in the cell. So these two efforts are very much related.
Mm-hmm. Grazie. Forza, adesso tocca a voi. Ci sono domande, curiosità? I microfoni? Oh, c'è una qui in seconda fila. Eccolo lì, perfetto.
Intanto grazie mille della presentazione, davvero super interessante. E volevo chiedere una cosa più relativa all'applicazione. Cioè, immaginiamo che davvero ci sia la possibilità di utilizzare questi Escherichia coli per produrre zuccheri o insomma per catturare la CO₂ e produrre zuccheri. Intanto come sarebbe da fornire loro energia per permettere questo processo e poi se crede che sia effettivamente qualcosa di realizzabile in termini di produzione di quella quantità di energia. Cioè, ipotizziamo che si faccia tramite pannelli solari. quanti pannelli solari servirebbero? Sarebbe effettivamente una cosa possibile? Grazie mille.
Okay, so first I'll say I need to get your details because maybe you want to work in the lab. This is exactly the kind of question that we were asking ourselves about what I've shown you is sort of like a proof of concept that you can achieve such a transformation. Something people didn't believe when we started working on it 17 years ago, although it seems like the people in the EU that needed to give the money, they understood it's interesting research, but most of the even scientists I was talking with felt that, who knows if anyone could achieve such a thing in the next 100 years or so. But now that we know that we're able to do that, comes the next set of questions of, how efficient is that? How do you supply the energy? What would be the cost of this? And so in terms of supplying the energy, there's several avenues. In the end, it's probably starting from some renewable source of energy, such as the sunlight. With that, you can produce electricity relatively efficiently, and that electricity could turn into all sorts of things that the cells could use, either hydrogen or formate or methanol or directly electricity. But the more challenging question is whether you can do all of this economically. So I actually have this in the same presentation. I have another 30 slides in hidden mode of like looking step by step at that, but I wasn't sure everybody's ready for that after lunch. And then we break down the question to see how efficient could that be. And the short answer, it's not so easy. It's problematic. It depends. If you remember in one of my slides towards the end, I was talking about the different products one could make. One is like, high-end food like meat and things like that, and fine chemicals like some of the industry here in northern Italy makes. For those, it could be quite competitive because it seems like you can produce things at the right price. When you go towards, bulk, like commodity foods, it becomes tougher because, even though we enjoy, the pizza made out of flour very much, we're not willing to pay so much for that flour. So there, even if the bacteria could make such a thing, it's not clear that it would be competitive. And then for the fuels, we're willing to pay even less, so it's even tougher. So I would say what you're asking is really the big next challenge. And it seems to me that even though we're not willing to pay now, I think in the future, we'll have to change our mind. Because it seems like our scientific analysis of using the resources means that things would have to change. What is true now would not be true in 20 or 30 years' time, maybe even in 10 years' time. We don't know exactly. Because otherwise, the accounting does not work.
Ingaggiato, devi mandare il curriculum, fatta. Prima della prossima domanda ne faccio una che è collegata a questa indirettamente, cioè tu sai che ci sono alcuni nostri colleghi che lavorano nell'ambito dell'ecologia che hanno paura che l'utilizzo, la realizzazione di batteri in laboratorio che poi vengono rilasciati in ambiente possono avere effetti non intenzionali, possono andare fuori controllo. Tu pensi che queste siano preoccupazioni sensate? Ci state pensando o pensi che siano eccessive?
Yeah, so definitely I think we should always, listen and consider each and every, concern that is related to such things. And at the same time, we should be evidence-based, science-based on thinking about, how much is the risk and what could be the alternatives. So the sort of thing that, we're considering and doing are the sort of thing that could not live in any way out of the lab. We have to supply them with the energy, we have to supply them with the right conditions, etc. So we really should, on the one hand, be careful, and anybody who raises such a thing, we're having a long discussion, and so far nobody came with any scenario that seems to be of such that is really something that is not handled. But I think there's another thing that we should remember, and that is the fact that doing nothing or not also has a very big price. The fact of the matter is that we are changing the planet and are changing the land and the composition and things like that. And that is something not hypothetical. This is something that is happening every day on a huge scale. And therefore, we need to find the balance of like, with new technologies, probably that would be where the solutions would come for. We should have regulation, we should be careful, we should think about how to do those things. But at the same time, we could not stop the progress forward because otherwise we're not in a situation that will be able to survive that way.
Sure. Prego, altre domande da parte vostra? Non mi inserisco adesso. Io vi vedo poco, ecco, adesso vi vedo. Non avete curiosità per Ron Milo sul futuro della sostenibilità? Allora Ron, intanto che se ne fanno delle altre, te ne chiedo un'altra io perché sei passato molto veloce, ma è importantissimo. Quando hai fatto vedere la curva della massa antropogenica che dal 1900 intercetta la biomassa nel 2020. Due cose. Perché la curva si impenna tremendamente dopo la seconda guerra mondiale. Lì è chiaro, no? Proprio diventa un andamento completamente fuori controllo e da lì in poi di cosa è fatta quella massa antropogenica, perché in fondo è la storia di 3 generazioni umane, dei miei nonni, dei nostri nonni, i nostri padri, noi e adesso ci sono i nostri figli, i nostri nipoti. È successo tutto lì. Cos'è successo in base ai calcoli che avete fatto? Tutto, è successo quasi tutto lì.
Yes, so I think it's a fascinating graph to spend time looking into, and we have versions where you could look also like at the rate of change, which is also very interesting. And there you can really see all of the big events, anything from the First World War, the Big Depression of the 20s and 30s of the previous century, Second World War, but also things like like the oil crisis of 1973, etc. And this sharp increase that you see after the Second World War is also known as the Great Acceleration. It's a time where indeed humanity, through, I would say, also thanks to technology, was able to increase standard of living and do industrialization on a much larger scale, build a lot of things. A major component is cement for our construction and building. So this is known as the Great Acceleration. It's also the suggestion for how to define when did we move from the previous geological era, known as the Holocene, to the current, which is known as Anthropocene, the age of humanity, because it's clear when you look at all sorts of properties of Earth that now something has changed. You start to see a new force, and that's humans, and this great acceleration that you're mentioning is suggested as to be the time point at which we moved into this new geological era, although there are other suggestions of different time points for that. So this is driven by increasing both population and standard of living and new ways to make stuff efficiently and cheaply around the world. Much of it is related to construction, but also other things. And then it's important to me to mention that this point of meeting at 2020, and since then there's more human-made stuff than the living things. It's important to mention that we're not specifically against it. As I told you, I have 3 daughters at home. We have a house. We have a car. I'm not against this. Obviously, we need this, and we're happy about having such things, as just like the nice thing that we see here in the town of Bergamo. So I think the message is not that we need to change that. I think the important thing is for us as humanity and society to be aware of the fact that now, as a force in the world, we now became on par with many, many other things in the living world, which means that we can't hide behind the claim that, there's millions of different species and the world is huge, so no need to worry. We could keep on consuming and doing things any way we want because the world is large and nature has so many different species. This figure and this study, which I think you're also helping promote, which I'm very happy about, tells us that we became a force on par and that we are reshaping things, and therefore we also have the responsibility to think how to do that. And maybe we're not changing, maybe we won't stop building and consuming, but we have to be aware that we have to do it in such a way that takes care of the other parts that are essential for our well-being. So in the end, it's really all about us in the sense that, I'm pretty sure that the Earth, a million years from now, or 100 million years from now, the world has lived through a lot of things. It will be able to, survive, flourish. There'll be new living things, whatever. But for our generation, for the next generation, for the following generation after that, our well-being and flourishing will depend on understanding these things and understanding that we're a major part in managing this planet. And in that respect, I think that curve helps to understand that message and hence its importance.
Sì, nella immagine della biomassa che hai fatto vedere, in particolare quella dei mammiferi, c'è un lato che non hai discusso e ti chiedo di approfondirlo perché è impressionante. Quasi il 60% della biomassa di mammiferi sono animali d'allevamento e come sappiamo gran parte concentrati in allevamenti intensivi. Ne hai anche qui intorno, qua nella pianura nostra ce ne sono tantissimi. Lì, stante il fatto, come tu fai vedere bene, che l'impatto ambientale che hanno, no? Questi allevamenti intensivi, alla luce di quello che hai appena detto, lì come è possibile secondo te fare la transizione? Perché dietro quegli allevamenti intensivi c'è una domanda economica, c'è un consumo delle persone che vogliono la carne, c'è dietro un mondo, ci sono interessi economici. Come si fa in quel caso a fare una transizione come stavi dicendo tu adesso?
Yes, so I think it's important to understand we have a huge problem, a huge challenge, and scientists could help, for example, in clarifying to us, to the rest of society, what is the situation, that is our obligation. For example, the environmental burdens that come as a result of our dietary choices, and how much beef do we choose to produce, which is not an efficient way to use natural resources. Now, the fact that we know those facts does not mean that we know how to solve them. We know how to show that, and we know how to clarify that. And now I think there's a much larger discussion that needs to be done. Within that, you need people from the social sciences, from the natural sciences, from the humanities, but also businessmen and farmers and many, many other people to try and see how do we solve the problem. So in that respect, I would say, I'm an expert on doing the calculations, showing the numbers, being able to tell that. It doesn't mean that I have all the answers to all the problems of how to go forward from here. We could tell what would be the implications of changing from this diet to that diet to be able to incorporate within our food things that are done in novel ways, such as those microbial production. But definitely we need many people in the room and in the discussion, and we have to make sure that people also have good education so that they could participate in that in an evidence-based, and I think that's the path forward. And in that respect, I think having a science festival is also very important. So really well done to all the organizers that have been doing it now for, I understand, like 25 years. And it's amazing. I don't think I've ever been in a science festival anywhere around the world which engages in such a beautiful way.
E ti chiedo una cosa proprio collegata a questa, io ne approfitto, qui Ron Milo, scusate, perché sei molto impegnato anche in progetti di comunicazione della scienza. E anche qui ti chiedo qualche suggerimento. Per esempio, sai che in Unione Europea si è discusso dell'utilizzo di proteine da insetti, farine di insetti, e subito politici italiani hanno cominciato a dire ecco, l'Unione Europea vuole farci mangiare i grilli fritti dalla mattina alla sera. C'è sempre questa retorica fortemente contraria a ogni innovazione sostanzialmente tecnologica o comunque di gestione, no, di questa transizione, che richiederà comunque dei cambiamenti comportamentali. Lì come si fa, secondo te? Quali sono? Mi raccontavi di un progetto di comunicazione della scienza sul climate change molto innovativo. Noi qui, ovviamente in Italia, lo soffriamo molto per gli eventi climatici estremi. Che suggerimenti state elaborando sull'aspetto proprio di cui ci occupiamo qui, cioè la comunicazione della scienza?
So on the one hand, I would say, there's many people and there's many views, and then there's also like many forces in parallel. So on the one hand, there's a lot of forces against such a transition. But then when I came to to talk about our research in Brussels, the things on the walls that I could see were all talking about the need for that. So I think it's nice to appreciate also that there's a lot of people that are in favor of finding new solutions and understanding that there is a challenge. I don't know exactly how it would unfold, but I think we have something very strong in our favor. Super strong. And that is the fact that, in our favor is something that does not care about, how the politics plays out and what somebody says in the US or in the parliament or somewhere else, and that is nature itself. Nature does not care about the arguments of whether we want to do this or want to do that. It really is based on, the rules of the physics, the chemistry, the biology, and then when the climate changed, it doesn't care what was written in the social media. So in that respect, even if there'll be all sorts of spins in one way or another, those that are studying nature, that are learning the laws of science, they have this very powerful things in their favor, which is truth. And I think that would prevail in the long run.
Yeah. L'ultima cosa, se non ci sono altre domande... Ah no, ce n'è una, poi la faccio io. Vai.
Grazie mille Ron per la presentazione piena di spunti interessanti. Una domanda sempre riguardante il futuro. Stai mostrato benissimo come stiamo cercando di copiare le leggi della natura, cioè cercare di riprogrammare i batteri facendo un po' quello che sappiamo già fare, no? La natura sa già fare. Si potrà pensare di inventare nuove macchine, nuovi enzimi per poter generare energia in maniera alternativa basandosi su cose che la natura non sa fare, per esempio magari dando come fonte alcune di queste cose antropogene tipo la plastica che noi sfruttiamo e che in qualche modo potremmo cercare di degradare per fare nuova energia.
Yes, so we're definitely working also in such directions of using what's known as side streams or waste of production of all sorts of things in order to feed them to bacteria in order to produce stuff that we enjoy. So this is definitely an effort. It's, there's many different labs approaching it in many different directions. And I think that would definitely also happen. Now it's a question of scale and economics, and it would not solve all of our problems, some of them, but this is definitely, we need to be more efficient. It's also part of what's known as a circular economy, trying to see how to reuse all sorts of things that otherwise we're wasting.
C'è una domanda qui da Bob Sitia, che tra l'altro ringrazio, Comitato Scientifico Bergamo Scienza, che ha favorito il contatto con Ron Milo. Grazie Bob, a te.
Meraviglioso, veramente interessante. L'aumento della massa di cose preparate dall'uomo significa immobilizzare delle sostanze che prima erano libere. Quindi, in un certo senso, i mattoni sono terracotta. Prima o poi la terra cruda finisce. Avete fatto questo calcolo?
Yes, so good news, we're not going to run out of Earth, at least not because of that. So what I was showing you is really the weight of living things versus the weight of human-made things. Now, the way many of those human-made things came, it's not from living things, it's not from forests that we cut, although that happened a lot as well. But let's say when you want to make concrete or bricks, you take usually all sorts of rocks, you crush them, and you add some other minerals, and with that you make concrete. There's much more concrete available to us, orders of magnitude more below our feet. So in that respect, we won't be running out of that type of building material anytime soon or even anytime further. So in that respect, we do have the capability to make, say, building material of that sort. Although, again, there's varying things. For example, in terms of sand, there's all sorts of locations around the Earth that we're running out of sand, and that's a big problem. But it's not the cake of such minerals is still very, very big. But as I showed, this really tells us the message of where we're standing, us, humanity, the rest of the living world, and how we became a very powerful entity right now, and therefore should be responsible in how we're affecting other things.
C'è una domanda in seconda fila qua, al centro. Arriva.
Io ho problemi di lingua, forse magari la mia domanda non sarà molto pertinente, ma pensare anche di ritornare indietro. Noi in fondo produciamo troppo, consumiamo troppo e praticamente molta roba che consumiamo va nei rifiuti o va gettata. Se abbiamo tutti questi problemi per questa CO2 si potrebbe imparare a ritoccare un poco il nostro stile di vita.
So I think going back is not exactly how I would frame it. I think I want to achieve some of those things of being smarter, how much we consume and maybe consume less, or maybe do it more efficiently, or thinking what do we need and what do we not need. But instead of that going back, I think we need to go forward and be smarter, more educated about that. Now, I'm not saying that this is exactly how things are moving right now. I think this is, what you're suggesting, what I'm talking about is where we need to move. And now it's a challenge of us as a society. We need a lot of science communication for that in order to show, okay, where would we go in one way and where would we go in the alternative way. So I think I would frame it as like, not necessarily going back, but, take some of the things that, we did once and in the future think how to incorporate it smartly.
Ron, ti chiedo un'ultima cosa, vedo che non ci sono altre domande, giusto? Un'ultima cosa, più mediatica se vuoi. Il tuo paper del 2020 è stato usato ed è una perfetta esemplificazione di che cos'è l'antropocene, no? L'impatto umano sull'ambiente. Pesiamo più della biomassa con i nostri oggetti, siamo diventati una forza geologica perché cambiamo proprio le regole geofisiche del pianeta. Sei rimasto deluso del fatto che l'antropocene è stato bocciato, non è stato introdotto nella carta geologica o non importa, lo useremo lo stesso?
Yeah, so I don't know if everybody knows this thing, that like when you want to change the name of a geological era, you can't decide to just do it. We're scientists, or the scientists that have the keys to the vocabulary, to the name, they have to decide on it, and these are the geologists that are giving the geological name, and they are very serious in doing this. They have many committees that look into this question, and the point raised here is the fact that in the most recent discussion, they decided not to change the name, not to make it official, but it's important to understand why did they do that. And in short, the reason is because they need to decide on the exact time and the exact indication of what should be the right time and reason for that. Now, it's very difficult because, as we discussed before, there is the great acceleration, this very fast increase that happened following Second World War. At the same time, other people say the right time to do it is the Industrial Revolution, when we invented, in England, the steam engine around Manchester and things like that, and started so this is a different time. This is not 1945. This is the end of sometime in the 19th century. then other people say, actually, we see indications of human impacts really when Europeans arrived in the Americas. And this had a very big shift. Some other people go back to the agricultural revolution and say, then it's when we change. So we scientists, we like to quarrel on such things. And this is, very, in my perspective, unfortunately led to the fact that they said, okay, we're not ready to decide between this, and that. We all are aware that we are changing the Earth and it's a different time. But because we can't decide on what time point it is, then we can't say right now that we give it this new name. Which again, from my perspective, it's unfortunate, but I think it also shows why, in terms of because it also shows why you don't want to leave everything just to the scientist in the room. This is something that, in terms of the name, maybe we could discuss, what the time point, but, as a society, we need to have people of practice coming to say, okay, we care about what to do about it, how to solve the problem, not about the question whether it's the agricultural revolution, the industrial revolution, or the great acceleration. So for that, we need to engage many other people and to move forward.
Bene, grazie. Io penso che Ron ci insegni come sia importante partire dai dati, no? Per poi condividerli e poi decidere che cosa fare. Questo è un segno di democrazia deliberativa, che è uno dei temi forti di Bergamo Scienza, quindi ti ringraziamo tantissimo di essere stato con noi. Thank you.